So in this example, we're going to see that water flows through a 2-inch steel pipe, and there you've been given an inner diameter and an outer diameter. The pipe then is heated on the outside by steam at 230 degrees Fahrenheit, where the overall heat transfer coefficient is 250 BTU per hour feet squared degree Fahrenheit, and that is based on the outside area of the pipe. If the inlet and outlet temperatures for a 1 foot length of pipe are 80 degrees Fahrenheit and 180 degrees Fahrenheit, what is the water flow rate? So let's maybe just draw that and see a bit more clearly what is actually going on. So it's saying that water is flowing through a pipe. So we're not going to worry too much just yet about the size of the pipe, but there is the pipe, and we have water which is coming through that pipe and out the other side. We then have heat, or this pipe is then being heated by steam. So on the bottom here, we'll just write steam, and this is being heated across this pipe. So this is how this pipe is now being heated. So they've said, what happens if we have a 1 foot section of pipe, where in this we have water that comes in at 80 degrees Fahrenheit and comes out at 180 degrees Fahrenheit. The question is now asking us, what is the flow rate of this water through this pipe rather? So the first thing that we need to realize here, and a little bit of a hint has been given here, is that they've given us the overall heat transfer coefficient. Writing it slowly here. Coefficient, they've given us this information as well, and they've said that that is going to be 250. 250, it was BTU per hour, square feet, degrees Fahrenheit. So that was a bit of a hint there. They've given us the overall heat transfer coefficient. So because of that, and we can see that the temperature, so something else that's different from our previous questions is that the temperature at the the left-hand side of the pipe and the right-hand side of the pipe change. So this is actually a heat exchanger question. It's not a typical heat transfer question. It becomes a heat exchanger question because one of our assumptions in heat transfer was that the temperature in and the temperature out were the same. Because this is not the case now, this is actually a heat exchanger question. So because this is a heat exchanger question, we are going to jump straight into the heat exchanger equation, which is going to be Q is equal to UA delta T log mean. So we need the delta T log mean in this one, and not just a delta T. The area that we are going to be using is the 2 pi r L. If we looked at the question, it said that the overall heat transfer coefficient is based on the outside. So that means this radius we're going to have is O, which I will use for outside. What we next need is going to be delta T log mean. So delta T log mean, if we remember, was delta T1 minus delta T2 divided by the natural log of delta T1 on delta T2. So now what we need to quickly figure out is what are the temperatures that we're going to need here, and then how can we fill this one in. So one of the things that was in the question as well was that the steam was actually at 230 degrees Fahrenheit. So we are going to assume that this temperature is the same on the left-hand side and it is the same on the right-hand side. So we're going to have 230 degrees Fahrenheit on the very left. So let's just highlight this quickly. So the steam is coming in at 230 degrees Fahrenheit with the water that's coming in at 80. It's then coming out at 180, and then on the right-hand side, the steam is still at 230 degrees Fahrenheit. That is the steam that's coming out, or that's after this one here. So what we need to know is, what is the steam out? The steam out is 230. What is the steam in? It is going to be 230 as well. So if we look at our equation, delta T log mean, our delta T1, we are going to have as the temperature rather, of the steam. I'm just going to write S, so that's the temperature of the steam in, minus the temperature of the water that is out. So that is going to be delta T1. Delta T2 is going to be the T steam, temperature of the steam out, minus the temperature of the water. Let's just try and keep these letters the same, TW in. That is then divided by the natural log of delta T1. So I'm not going to write that out again. It's getting a little bit messy. of this term at the top there divided by the term on the right. If we put the numbers into this now, we will simply have, sorry, let's change that back to black. We will now have 230 degrees Fahrenheit minus 180 for the water out, minus the difference of the 230 water out, minus the 80 degrees Fahrenheit, the water in, divided by the natural log, and we said that was the top to the left. That's 230 minus 180 divided by 230 minus 80. And I'm going to ask you to trust me. We do the numbers on that. That is equal to 91 degrees Fahrenheit. So that will be the delta T log mean of this one. What we're wanting to do now with that delta T log mean is go back to Q is equal to U A delta T log mean. We can now take the numbers from the equation. So that was 250 for the overall heat transfer coefficient. We're now going to multiply this by the area. So the area is 2 pi ROL, so it's 2 times pi. Let's just go and see what the value of this was up top here. So just if you're not aware of it, ID is internal diameter, OD is the outer diameter, so we said it's based on the outside area of the pipe, so we want this 2.375 inch, the two little markings there for inch, 2.375, so if we come back to the calculation, it's going to be multiplied by 2.375. That was diameter though, so we need to divide that by 2 to get us to radius, multiplied by 91 degrees Fahrenheit. If we then put all of those into a calculator, our Q value is then going to be equal to 14145.35. And I haven't included it here, but please, if you see the end of the video, you'll see the full work solutions for all the units. That is BTU per hour. We are going to want to convert that into kilojoules per second. And the unit conversion for that, we're going to have 1 kilojoule per second at the top, divided by 3412 BTU per hour. And again, you'll just have to check the maths on that one, and you end up with 4.146 kilojoules per second. I'm just going to ask you to double check that I've done the unit conversion correct for the hours and the seconds. Okay, the next step. If we just quickly go back to the question, it actually asked us, what is the flow rate of the water? So we actually don't want to know what is the energy, we want to know what is the flow rate of this system. So to get that, what we are actually going to now look at is an energy balance. So very quickly, the energy balance that we are going to need, we have du dt, see with the sum of the H terms, I'm not going to worry about the kinetic and potential energy, plus Q plus W. If we do this very quickly so that I can get down to what I need to do, no, it's at steady state. There is no W, there's no work term that was assigned to this. So what we're left with is that the delta H, and this is of the water that flows through that pipe, is going to be equal to the Q term that is coming in from that steam. Okay, we just need to check the signs when you do the maths here, but I'll leave that for you to check while you're doing this yourselves. Okay, so just to clarify here, this is the energy balance of the water in the pipe. So this is what we're ultimately going to solve for. What we've already got, if I scroll back up here, we calculated the Q, let's just change colors here, the Q because of the heat exchanger. So this down at the bottom is the Q from the heat exchanger that goes from the steam to the water in the pipe. So because energy is conserved, any heat that is lost by the steam is going to go into the pipe. So that value 4.146 is also equal to that Q there. So that is also the Q that we've already solved for the heat in the pipe. However, as I said, we are only worrying about now what is actually happening in the pipe itself. So in the pipe, let's come back on this side quickly. We said that in the pipe, we've got water at 80 degrees Fahrenheit and it comes out at 180 degrees Fahrenheit. So we have, let's put this on, water comes in at 80 degrees Fahrenheit and it goes out at 180 degrees Fahrenheit. So what we're actually wanting now is to find out what is the enthalpy of the water so that we can solve the equation on the top here. My version of the steam tables do not have degrees Fahrenheit. So very quickly, let's just look at a unit conversion. Okay, so I'm not sure you can see that, but there I've entered into just a unit conversion quickly. 80 degrees Fahrenheit is equal to roughly 26.667. So I'm going to make this a little bit simpler for us today, and I'm just going to call it 27 degrees Celsius. If you want to be a little bit more accurate, you could obviously go into the decimal places, but you'll see now why it doesn't really make that much difference. And very quickly again, you can see 180 degrees Fahrenheit is 82.2222 degrees Celsius. So we'll leave that as 82 degrees Celsius. So those are the degrees Celsius temperatures for the inlet of the water and the outlet of the water. What we're going to want to do now is to go and find a steam table. So here's the steam table booklet that we're going to use. Thermodynamic and transport properties of fluids, Rogers and Mayhew. And if I go and look, I need to go and find what page it is. On page 2, we can now find the steam table value for these temperatures. So we said the first one was at 27 degrees Celsius. So 27 degrees Celsius, I don't want to write in my book here, so you're not going to see the top of this at the moment, sorry. But this column here is going to be the enthalpy of the fluid, the HF. So that is where this liquid is still water. The question said water went into a pipe, so it didn't say steam, so we're going to assume it's all still water. So that means at 80 degrees Fahrenheit or 27 degrees Celsius, the enthalpy is 113.1 kilojoules per kilogram. If we now look for 82 degrees Celsius, and we come down to 82 degrees Celsius, we see that there is no 82 degrees Celsius. So I have a value for 85 degrees Celsius, which is sitting at 3559. So let me just write this in my notes. So at 85 degrees Celsius, we have an enthalpy value of 355.9. And if we come up one row, you'll see that at 80 degrees Celsius, we've got 334.9. So 80 degrees Celsius, 334.9. And that for both of them is in kilojoules per kilogram. What we want though is to take these two and interpolate. So I'll let you interpolate to find what do we have at 82 degrees Celsius. If your maths is the same as mine, you should get a value of 343.3, and again that's kilojoules per kilogram for the enthalpy of the water out. Okay, so we're now going to go back to the equation of the delta H of the water is equal to the Q term. This delta H of the water is going to be equal to the mass times by the difference. So this is the total enthalpy now becomes, let's just show you again, the delta H becomes the mass multiplied by the specific enthalpy of each of those terms. So it's going to be per kilogram. So it's going to be the enthalpy of the fluid at 82 degrees Celsius minus the enthalpy of the fluid at 27, sorry, I don't know why I'm writing that. The enthalpy at 27 degrees Celsius is equal to the Q, which we calculated earlier on. So simply that becomes M is equal to Q divided by that difference in enthalpy term, which I'm not going to write out in full. If we start putting numbers in, the mass, well, this is mass flow rate, so it's going to be mass per second, is now equal to 4.146 kilojoules per second. So that was from the heat exchanger part of this question, divided by the difference in enthalpies. So this is going to be for me more than you. Those two enthalpies were 343 and 113.1. So it is 343.3 minus 113.1, and those are both kilojoules per kilogram. If we then do the maths on that, that is equal to 0.01801 kilograms per second. And if you want to take this back, you can do the unit conversion back into the units that we had before. This will equal to 143 pounds per hour.